Good day, grade 12s. Today we're going to be looking at rates of reactions part 5, specifically the factors that affect rate of reaction. Now when we were busy with our Zoom the other day, I briefly chatted about the factors that affect rate of reaction, and today we're going to be looking at that in a far more detailed manner. So there are various factors that affect rate of reaction, and we're going to be looking at that now. Okay, so when we talk about the factors that affect rate of reaction, we're actually talking about things that affect collision theory. Okay, so these are the things that actually cause a chemical reaction to happen more effectively. I used a very, very simple analogy while we were busy doing the Zoom, where I said that if you wanted to cook some potatoes, you would do the following things in order to speed up the process. So you would firstly make sure that your potatoes were cut into small pieces. You would make sure that your stove was on the highest setting, okay? Those are things that you would do in order to make this happen faster. So when we talk about the factors affecting reaction rate, the first thing that we need to talk about is the fact that the nature of the reactants is quite important, okay? The concentration of the reactants is also something that we need to pay attention to. This one, state of division, that's the idea that we spoke about with the potatoes. The temperature is also something we discussed. And then the last idea we're going to talk about is the use of a catalyst. Okay, so we're going to start by looking at all of these factors now. The first thing, nature of reactants, is a very interesting idea because different substances react at different rates. So substances that are ionic are usually far greater or far faster at reacting than those that involve compounds. Okay, organic reactions are very, very slow. And then the thing with metals is, when we looked at the periodic table in grade 10 and grade 11, we know that there are very, very reactive earth metals. We know that if we take the group that involves lithium, sodium, and potassium, that potassium is the most reactive, and then the sodium and then the lithium being the least reactive of that. That is just the nature of an actual reactant. So there's not very much we can do about that in itself. Okay. Now, the next factor that affects concentration of reactants is concentration. Okay. So when we talk about reaction rate and we're talking about the concentration of reactants, we know that concentration can be calculated by using the formula concentration is equal to the number of moles over the volume that we have. So we already know that when we talk about the concentration of reactants, the number of moles plays a huge role in all of this. And this just means how much substance do we have in a specific volume of space. So if I take a volume of space, if I only have 2 reactants in it versus another volume of space that's similar, but I have, let's say, that many particles in it, we know that that's my higher concentration, and that's going to lead to a higher rate of reaction. Okay. When the concentration increases, it means the number of particles increases, and it also means that there are more collisions that can occur. Now, this concept, it should make quite a bit of sense. If you put more people into a room, the likelihood of those people bumping into each other increases, as you increase the number of people in that room. So it's the same with particles. The more particles you put into a specific space, the greater the chance of them actually bumping into one another. And then what also increases, just because of the fact that we are upping our odds, is that there's a possibility of correct orientation, all right, with sufficient energy. That also increases. So because you've simply got more participants in the pool, so to speak, there is a greater chance of a correct orientation collision as well as a collision with sufficient energy. And remember, these two concepts are the two concepts that are important for reaction rate, because collision theory says that I must have the correct orientation and I must have sufficient energy for each of the particles. Okay, so that means that the reaction rate will increase and more effective collisions will take place if we have an increase in concentration. So this picture that I have here, you can see that at a lower concentration, we have fewer particles in the same space, and at a higher concentration, we have more particles in the same space. These are all gases. Then when it comes to concentration like this, we've got a lower concentration versus a higher concentration, and that's if one of the reactants is an actual solid. Okay. The next factor that affects rate of reaction is actually the surface of the reactant that we are talking about. It's referred to as the degree of subdivision or the state of division. Okay, it means what sort of surface area are we actually working with. Now, this is quite a tough topic, or quite a tough concept to wrap our heads around, because we sometimes feel that a substance that is a solid will have more surface area than a substance that is in powdered form. But I would like to draw your attention to the fact that if we take a solid substance, okay, so if we take a perfectly solid substance and let's say something like that, a tablet, okay, what that will then mean is that it's only the surface on the outside of this tablet that makes contact with everything else in order to react. But if we crush it, we've actually got literally thousands of teeny tiny particles, and each teeny tiny particle will have its own surface area, which means that that's why the surface area increases when we actually crush things, okay, or break them into smaller parts. Even though it's smaller parts, there's more surface area available. Now, in a solid, the collision only occurs on the outside of that solid. That's what I was talking about with my example. Or on the exposed surface. But when the solid is broken up into smaller pieces, the total surface area becomes greater. And as a rule, the rate of reaction will increase as the surface area. So the rate of reaction will increase as the surface area increases when the solid is divided into smaller pieces, which is really, really useful, because what a lot of scientific processes do is, instead of using a solid piece of metal, they will use metal granules or something like that, okay, to affect the rate of reaction. The next factor that affects rate of reaction is, in actual fact, temperature. And it's one of my favorite factors because it's really, really easy to wrap our heads around, and it's a really easy way of actually improving the rate of our reaction. So a definition that you should be familiar with is that temperature is the average kinetic energy of a substance. Okay, so what that means is that if you take all of the particles within a substance and you measure their kinetic energy, the temperature of that substance will be the average of what you've taken. So when we talk about temperature, obviously when we increase the temperature, what will happen to the particles? This is a concept that goes all the way back to grade 8 and 9, or even grade 7, that when you increase the temperature, according to the kinetic theory of matter, the particles will move faster. Okay, that means they move around more. Because they're moving around more, by nature of that, they will simply collide more often. And because they're moving around faster, they're going to collide harder, which tends to increase the number of effective collisions. Okay, and then more particles possess enough kinetic energy to overcome the activation energy. Now, I showed you the Maxwell-Boltzmann distribution curve the other day, and this is another one. So what I want you to notice is there are two parts to this. There is a distribution curve that does not involve temperature. So that's this one over here. If you see, it's the one with the dotted line. So this is the Maxwell curve for just normal temperature. And then you'll see this curve over here is one where the temperature has been increased. And what you'll notice is that there are more particles, all right, within that space that allows for effective collisions, simply because we've shifted the curve. Okay, so we've shifted the curve into that zone. You remember that this is the point where we've got enough activation energy. So by increasing the temperature, we actually move the curve over so that there are more particles that lie within this range of effective collisions. All right. So the speed of the reaction increases when the temperature increases. That is the conclusion from temperature for effects on rate of reaction. Okay. Now, the last factor that affects rate of reaction or how fast a reaction occurs is referred to as adding a catalyst, all right, or the addition of a catalyst. So a catalyst is a substance that influences the rate of chemical reaction without actually getting involved. Okay, catalysts don't really get involved in the sense that they do not shift their own chemical properties. So there's no permanent change to them. Sometimes they get involved and some parts of things change, but there's nothing permanent that actually happens when to an actual catalyst in a reaction. In other words, you're going to get the catalyst out of the reaction exactly as it went in. So a catalyst increases the rate of the chemical reaction, all right? And the catalysts are not able to actually start the reaction off. So they're not actually able to kick the ball off in terms of get the ball rolling with the reaction. The catalysts take part in the reaction but remain unchanged overall. The mass and the concentration will therefore be the same before as it is after. And a catalyst provides what we call an alternative route for the reaction energy, or an alternative route for the reaction with a lower activation energy. In other words, what a catalyst does is provide a reaction pathway, all right? A reaction pathway that requires less energy. In sort of simple terms, you could almost refer to a catalyst as a matchmaker. In other words, if you have two particles that are needing to react, let's say we've got our two particles, one there, and one there. What a catalyst does is a catalyst simply provides a pathway between the two that's a little bit lower in energy. So it doesn't get involved, it acts like a matchmaker. Okay. Now, we all know these energy profile graphs from endothermic and exothermic reactions. So on this graph, what we have is, we have our reactants on this side, okay? We have our products on that side, right? And we've got our energy change over here, or sorry, our delta H on this side, the change in the energy. Now the top profile, in other words, the graph that does this on the top here, this is an uncatalyzed reaction. In other words, it's the reaction without the catalyst involved, okay? An uncatalyzed reaction. Whereby, if we look at the reaction profile when we include a catalyst, do you see how much lower the curve is? Okay, so the curve is much, much lower. And what this has actually done, which is quite fascinating, is it shifted the activation energy. This was the original activation energy for this particular reaction, that long line over there. And now the activation energy has shifted so that we actually have a much smaller activation energy as represented on this side over here. Okay, so we've got a much, much smaller activation energy. And that means that less energy is going to be required to put into the reaction before it actually starts work. So in terms of collision theory, what this means is that when we introduce a catalyst, we have more particles that have enough energy if the activation energy is less. Okay, so that means there'll be more effective collisions. I've got a diagram at the bottom, so I just want to draw your attention to all of the words, and then I'll show you the diagram. So what the diagram does show is how the addition of a catalyst decreases the activation energy. Okay, I'm just going to skip to the picture. This is another one of those Maxwell-Boltzmann distribution curves. Okay, now you can see that on this particular distribution curve, the curve itself doesn't shift. So we've got this curve and it's absolutely perfect and it's fine. And usually this is the point over here where something has everything on this side of the curve, on this side, okay, everything on that side has enough energy to actually react. But what we do when we add a catalyst is we actually shift the point closer to the origin. Okay, we shift that place marker closer to the origin, which means that at this point, because we've lowered the activation energy, all of the particles from this point all the way through now have enough energy to actually react, which means that adding a catalyst is a very, very effective way of lowering activation energy and hence increasing the rate of the reaction. So So the energy of the particles does not change with the use of a catalyst, all right? A catalyst arranges the reactant particles so that more effective collisions can take place. So it's really, really about orientation. As you can see on this, less activation energy is therefore required. Now, those are all of the factors that affect the rate of reaction. I'd like very much for you to create a note using the PowerPoint that I'm going to upload alongside this video. Have a great day, Grade 12s.